All right, so today we're going to be looking again more specifically at continuous functions, and the idea of a limit, the thing that we were talking about the last time, it kind of continues on into this section, and it's kind of important because unless we have a really good firm understanding of how limits work, then we really can't have a really full and complete understanding of continuity or continuous functions. One thing I want to point out really quick is that when we look at these notes here, in section 9.2, there's actually two topics that they talk about. We're going to completely ignore the second topic, which is limits at infinity. We're just going to completely ignore that. We're only going to be looking at the continuous functions part. So if you look at the textbook and you're like, man, there's a whole lot of this textbook or this section that we haven't really looked at, that's intended. So I just want to give you a heads up about that. So one of the things that I do want to go through is to understand the definition of what a continuous function is, okay? A continuous function in real simple terms is you have a function that doesn't have any holes or jumps at the particular point that you're looking at, okay? So specifically speaking, if we look more formally, there's a full-on definition. It's continuous if and only if the limit of f of x is equal to f of c. And so what do I mean by that? These are the three things pretty much it means. Number one, that the function evaluated at that particular value of c, it exists, that the limit itself exists, and that the limit is equal to whatever that evaluation is. So let's go ahead and take a quick look here at this graph, okay? And I actually have a little table that's kind of corresponding to the graph down below, so you can kind of see what happens. So as we trace along this graph, you'll notice that when we get to 1, the function evaluated at 1, which in this case, that's our c value, okay? The function evaluated at 1 is going to equal 2. The limit is the same thing as the function evaluated at that point. The limit is also 2. So because of that, because the function evaluated at that point is the same as what the limits are from the left and from the right, or the general limit, right? You can think of it like that. Because those two things are the same, right there, the function is continuous, okay? So, and I want to be very specific here. When we talk about continuous and discontinuous functions, or functions that are not continuous, we have to specify where that happens. So the function f of x is continuous at x equals 1. Now let's look at 2. At x equals 2, what happens is I have a hole there, okay? So because of that hole, the function is not continuous. In fact, you can actually, if we look at the formal definition, f of c, so remember c is going to be 2. When I evaluate the function at 2, it's going to actually equal 1. So I don't know if you can see my cursor here. Let me click here. There we go. So at 2, you can see that the function is equal to 1. However, the limit is going to be 2. So because the limit and the function evaluated at 2 aren't the same thing, right there, that's the very definition of what it means to be discontinuous. So the function is continuous at 1, discontinuous at 2. At 3, take a look at what happens here. There's a jump, right? It jumps from 2 down to 1, so therefore it's discontinuous there as well. And then at 4, it's the same thing. There's a hole, so it's also discontinuous. So the only place, I should say, this function is continuous every single place except for x equals 2, x equals 3, and x equals 4. Every other place on this function, so at 0, it's continuous. At 1.5, or 3/2, it's continuous. At 2.5, 2.5, it's continuous. So we generally identify functions, their discontinuity, just at specific locations, we don't say, oh, it's a discontinuous function. Well, okay, you have to be a little more specific. Where is it discontinuous? It could be discontinuous everywhere or in just certain places. So in this case, it's just discontinuous in certain places. So let's look at the chart here. So I wrote down the c value, which in this case is 1, 2, 3, and 4. So the c values that we're choosing, the function evaluated at that c value. So at 1, the function is going to be 2. the same thing goes with the limit. So what the limit is at c equals 1, which is going to be the same thing. In this case, it's going to be 2. If we look at 2, the limit is going to be 2, but the function evaluated at 2 is going to equal 1. So there's a difference there. So generally, any place that you see a difference between these two values is where there's a discontinuity. For 3, the function evaluated at 2, or sorry, for the function evaluated at 3 is going to be 2 because that's where the closed circle is. The limit does not exist because, again, there's kind of that jump between the two. And then for the fourth one, there is no point indicated. There's no closed circle anywhere, so therefore it's undefined. And the limit, though, however, would be 2. So I would probably go back through that if you're confused. Just take some time and kind of absorb the information a little bit. And really, this information down below is kind of a recap of what I just covered. But I want to talk a little bit about this paragraph here where it says, so which functions are continuous? In fact, every function that you've ever studied is continuous where it's defined. So functions that have asymptotes, we generally say x cannot equal whatever the value of the asymptote is, okay? That means that every other place is defined, so it's continuous everywhere else, except for that place, where the asymptote lives. So the function's continuous pretty much everywhere it's defined. It's polynomial functions, radical functions, so that means ones with square roots, rational, fractional, I guess, functions, exponential and logarithmic functions. They're all continuous wherever they are defined, so wherever their domain exists. Moreover, any combination of continuous functions is also continuous. Okay? The nice thing about that is it's helpful because the definition of continuity says that for a continuous function, the limit has to equal whatever we evaluate at that particular point. Okay? So we can find the function by directly substituting, kind of like what we did the last time when we had a polynomial function. We were doing a substitution. It's the same idea. We can find the limit by direct substitution or evaluating the function if the function is continuous at that point. So what I want to do now is I want to go through some examples to kind of illustrate what specifically I'm talking about with how we can go ahead and solve many of these problems. Okay, so let me go ahead and switch over here to my whiteboard, or blackboard, I guess. So just as a reminder, I'm going to write these conditions down. So remember the conditions. Okay. In particular, I'm just going to be looking at limit x goes to c of f of x is equal to f of c. Okay? So this is like the main condition here. The other ones, yeah, they're part of it, but this is really like the biggest condition that we really need to consider. So let's go ahead and look at this. So suppose I've got f of x is equal to x squared minus 6x plus 8 divided by x squared plus x minus 20. And my whiteboard is being very, very laggy right now. And here they specifically say, by the way, that x cannot equal, or they're actually asking us to figure out if it's continuous or discontinuous at x is equal to 4. Okay? So the very first thing that we do, and just like we did the last time, is we're going to check the denominator. Okay? So check the denominator. Okay? So if I substitute f of 4 into the equation, I don't really care about what's going on up in the numerator. I only care about what's happening in the denominator. So if I sub in 4, I'm going to get 4 squared, which is 16, plus 4 minus 20, which you'll notice I get a whole bunch of stuff in the numerator. I don't really care what that is. and a 0 in the denominator. So in this case, it is not continuous at x equals 4, okay? Because we get a 0 denominator. So the function is not continuous at f of 4. So not continuous. US. All right. Let's go ahead and do another one. I'm going to do a piecewise defined function on this one. So let's go ahead and take a look at f of x. Oh my gosh, this lag is like driving me nuts. X squared plus 1 and 2x squared minus 1. Now notice, since it's piecewise defined, it means that generally there is the possibility, I shouldn't say generally, there is the possibility that there's a gap between one function as we transition to the other one. So this is for x less than or equal to 1, and then for this one, this is going to be for x greater than or equal to 1. Or greater than, sorry, not just greater than or equal to, just greater than. Okay. And of course, they're asking us to determine if it's continuous at 1, which, yay. So let's go ahead and figure out f of 1, okay? So where f is equal to 1, we're going to be using the top one. So x squared plus 1, this is going to be 1 squared plus 1, which is equal to 2. Okay, and then on this problem, to determine the limit, my suggestion would be just to go and use the left-hand limit and the right-hand limit, because since we have multiple pieces here, we can do the left-hand limit at 1, and we're going to use the top function, and the right-hand limit, we're going to use the bottom one. So if I do the limit as x goes to 1 from the left, if my stylus will work, of f of x, this right here is the same thing as the limit of, I made a mistake, of x goes to 1 from the left of the very top function, x squared plus 1. And since this is a polynomial, we can just evaluate. So 1 in there is going to be 1 squared plus 1, which is equal to 2. Okay? So the left-hand limit is the same as the function evaluated at 2. Hopefully, the right-hand limit is also going to be 2. If it's not 2, then we have a problem. So in this case, the limit as x goes to, come on, 1 from the right of f of x, in this case, is the limit as x goes to 1 to the right of the bottom function, since we're coming from the right here. For all values bigger than 1, we're coming from the right. So that means that this is going to be 2x squared minus 1, which is equal to 2 times 1 squared minus 1, which in this case is equal to a, what, positive 1? So this is a problem, okay? So the conditions, you can kind of run down the conditions if you look back at the notes. Does the function exist? Yes. The function exists at that point. We can evaluate it at 1, and it equals 2. The left-hand limit in this case, so the second condition is, does the limit exist? Since the left-hand limit and the right-hand limit are not the same, the limit technically does not exist. So therefore, condition 2 is not satisfied here, which means that because these two things right here do not match with this thing right there, this is a discontinuous function at x equals 1. So it's discontinuous. Continuous at x equals 1. Okay. All right. Let's go ahead and do another one. I want to do one that's a little bit more kind of like an application question. So if we look at the applications in particular, you're going to see a lot of different things. So I want to read this question, and hopefully this will, we can kind of write down some information about this particular problem. So let me turn to the page, that would be helpful. This is regarding kind of like an economics or business kind of situation or scenario. Suppose the demand for a product is defined by the equation. So we have P is equal to 200,000 divided by Q plus 1 squared. Okay, that's a 2. I'm sorry, my computer is having some nice challenging difficulties right now, and I'm not really sure why it is, but in any case. So in this case, P is the price. P is price. And Q is going to be the quantity demanded. Okay. So here's what we're going to do. The question asks us for part A, is the function discontinuous at any value of Q? And the question is, which value? So this is kind of where it goes back to determining the domain. Okay. If you remember back a few sections ago, we talked about some of the rules for the domain and places that the domain does not exist. So one thing you'll remember is if you take the denominator, it's going to be the value for Q which causes this denominator to go to 0. In this case, I think it's pretty obvious. It would be Q is equal to a minus 1. If Q is minus 1, that's a plus 1. Then I have 0 squared, which is 0. So in this one, you can kind of do it just by, looking at it. So this is part A. So at Q, come on, Q is equal to 1. It's discontinuous. Continuous. Okay? So that's literally part A. In other more complicated problems, you're really just going to be looking at the denominator and setting that equal to 0 to figure out what's called the critical value, or where that asymptote or hole exists. It could be potentially either one. So again, we're essentially trying to figure out all the places where it won't work. Okay. Part B is going to be, this is what it says. Because Q represents quantity, we know that Q has to be greater than or equal to 0. Is the function continuous for any quantity or any Q bigger than 0? So let's actually go ahead and graph this. So I'm going to go ahead and switch over to my browser here. Let me go and pull this up. And give me just a minute. And we'll fade this so it's this. Okay, so let's go ahead and substitute in our equation. So we're going to have y, I'm just going to do y equals. So y is equal to 200,000. That's 20,000. 200,000 divided by, and we can do x plus 1, close the bracket, raised to the second power, and it's going to graph it. And you'll notice that my graph doesn't show up. So what do? I have to go way out here, okay? So you can kind of see what happens. This is the graph that we're looking at. Because Q represents a quantity, we know that Q has to be bigger than or equal to 0. Is this function continuous for everything? So the question is there any quantity specifically that we throw in here that's positive? So in the previous part, we noticed that we had Q at equal to, oh, it was minus 1, sorry. So I'm sure, see, this literally like, this whiteboard like being slow for me is like causing, see, I'm trying to erase right now and you can see nothing is happening. It's like so annoying. So I'm going to have to fix this. I'm not sure what's going on with it. This right here is supposed to be a -1. Sorry, that should have been a -1. So in this case, Q greater than 0, this right here is the only thing that would cause this to not exist. So you can pick any Q value, no matter what it is, and you're going to have a continuous function across the board. So in this case, because Q represents quantity, we know that Q has to be greater than or equal to 0. Okay? And the answer is yes, this is continuous. This is continuous. For all Q bigger than 0. Since no value. Will cause this function to be undefined. Okay? So that's kind of the idea for like a more kind of specific question. So for continuity, it's again kind of an extension of just really what we've been looking at prior to this lecture, especially the previous section of content. So that's really it. That's all we have today. And if you have any questions, again, don't hesitate to let me know. And I will be seeing you next time.